All right, guys, so we're going to kind of pick up right where we left off with the last video. So we finished the shear moment diagram part of this topic, and we're going to move on to bending deformation of a straight member, and we're going to derive the flexure formula. Okay, so once again, just like we did for torque and torsion, shear stress, right? How we connected these two, we derived that equation. We're going to do the same thing for moment, internal moment on a beam, and sigma or normal stress, okay? So I'm going to start off by drawing kind of a 3D element here. Best I can. There we go. Alrighty. And let's define our axes. So this would be my x-axis, kind of right there. This would be my z-axis, kind of parallel to this portion. This would be my y, parallel to this. Okay, so we've now defined all three of these, this 3D system, okay? And I'm talking about bending, right? When I'm talking about bending, I'm talking about some moment applied to the z-axis. Okay, so let's draw the length here. This is the length of my element. Okay, and it's super important, and let me write that this is the x-axis. It's super important that we understand the difference between torque or torsion and moment, okay, and what's happening here. This is kind of hard to, let's see if I can describe this when you're not seeing what I'm doing, but let's say you have this block that I just drew in your hands, okay, and you're curling your fingers towards the center of the block, and your thumbs are pointing your face towards your face, okay? You're curling in. That bending is bending along the z-axis. You can see how you're curling your fingers along this axis I just drew, right? Curl your fingers along this axis. Your thumbs will either point kind of out or in, right? So you guys kind of see how that's happening. They'll point towards your face or they'll point away from your face, right? That is MZ. That is applied moment about the z-axis. Whereas for the x, you can see now you're twisting your hands around that long axis. You cause that twisting motion, okay? So try your best to kind of understand what that looks like. You can do it in your, do it on your hand. Try moving your hand in those directions, or your arm, sorry. And if you don't get that, post it on the discussion board so we can kind of discuss it and talk about it and see what that looks like, okay? So let's continue here. And I'm going to draw, basically, this is kind of like no load applied right now, right? I'm going to draw a really exaggerated version of this after we have subjected it to some bending. Actually, let me redraw that. Okay. And you can see when I bend this, the top experiences, right? This top portion, it shortens. It becomes shorter. And this bottom portion becomes longer. So the top is in compression and the bottom is in tension. We're pulling on the bottom there. So we're going from tension to compression here. We're going from long to short. So at some point in the middle, we're switching from tension to compression, going from long to short, and we're going to hit a length that's the same as L, okay? Unchanged length. And we call this our neutral axis. Okay, we have no length change on that portion, okay? So even after bending, our neutral axis stays at the same, okay? And just so we're clear here, let's put a little side note. This derivation is for cross-sectional areas. Let me write this down. That are 1, symmetric about the perpendicular axes to the NA. That's 1. okay? And 2, the resultant internal moment acts about the neutral axis, which is how we kind of drew it right there, okay, about MZ. All right, so let me draw the cut that we're going to make, right? So this is some cut, okay. I'm going to cut here, okay. And we're going to come down here, and I'm going to kind of zoom in on this cut. Okay, so what happens when we zoom in on this cut? I'm going to take this to 2D now. Actually, let me draw this a little bit bigger here. Okay, I'm going to take this to the 2D. And this is before loading. You can see nothing has changed. Right? This is the location of our neutral axis. Right? And we'll define this length here as some delta x. Okay, we made a little cut. So some small delta x, some differential element. And we're going to define some arbitrary line segment maybe here because we want to see what happens when we subject this to bending. And I'm going to call this delta s. And we can see that delta s is just equal to delta x before loading. Okay, this is just a line segment. Okay, and we'll say that the distance that this line segment is from the neutral axis, we'll call it y. So y equals distance from NA to line segment. This could be any distance, right? So, and then this here, one more length we'll define. From the NA to the extreme top, this compression fiber we'll call C. And C is our extreme distance from NA to outer side. Okay. Now, what we're going to do is we're going to see what happens to this element after loading. So we want to see what happens after we apply that moment. What happens, and we know, I kind of drew it earlier for you, we know that we experience, this is very exaggerated just to show you, some bending of that element that looks like this. And we're going to come back in here and we're going to say, well, we also know that this is my NA. And what's the length of the NA? It doesn't change. So if it was delta x before, it's still delta x. And let's draw that line segment above. This line segment now has a new length. We'll call it delta s prime because we know the top is compression. And can you guys tell me, is delta s prime shorter or longer than delta s? Think about this. It should be shorter because the top compresses. Okay. And our NA, again, just to be super clear, our neutral axis remains unchanged. Okay, so still delta x. All right, so we want to now look at what's happening to this system, and we can kind of see this is like the arc of a circle. So we could actually define this by some circle, you see. Okay, I'm going to erase that, but you see what that is. So the way we're going to define this is that this arc acts around some center. Okay, I'm going to put the center O. And O is called our center of curvature. It's really just the center of our circle. Okay, and if I have a center, that means that I have a radius. So I'm going to define the radius from the neutral axis to O as rho. This Greek letter rho, this is just the radius. But we call this the center of the radius of curvature. Okay. Now we're going to put in our previous values. It's the squiggliest line. Let me fix that. Okay. We're going to put in our previous values. C is to the top of this element from here to here, okay? Let me rewrite this so it looks a little better. Hold on. Okay, C is from the top here to here. And then this is rho, the purple line, okay? And then again, we can still define Y, which would just be from here to here. This is our Y, that distance Y, okay? And then you can see also, if we wanted to define rho minus Y, the distance from the center of curvature to that arbitrary line segment here, the blue one, this would just be that whole length rho minus Y. Okay. Okay, and this is after loading. So now what we can say, we can use arc length, right? We can use arc length to say that delta x is equal to rho delta theta, delta s prime is equal to rho minus y delta theta. Okay. And we see that whenever there's length change, remember this, whenever I have length change, I have new lengths, I want to relate this to normal strain, because what is normal strain? It's delta L over L, and in this case, we would have delta S prime minus delta S over delta S, and we know, we'll just plug in what we know here, rho minus Y delta theta minus rho delta theta all over rho delta theta. Okay, we know a couple of things here. We know that delta S is really just delta X, which is my original length. Okay, and we can cancel these delta thetas, and we basically get this strain as Y over rho. Okay, and we're going to now see, we can see that our normal strain just varies linearly throughout the cross section. So normal strain varies linearly along the cross section. Okay, so what does that look like if we're going to draw it out? Okay, let's get this set up here. Okay. Let's start by drawing the deformation. Okay. So we know the top experiences this compression. We know the bottom experiences some tension, and if we connect those two, this is now the location right here in the middle where we experience nothing, basically no change in length. That is our neutral axis. Okay, and we can do the same thing for strain. We can draw our strain profile. And we can say, well, we know the top experiences compression, that would be negative strain. We know the bottom experiences this tension, that would induce positive strain, and we can connect those two again. They vary linearly. This is Hooke's law going through the neutral axis. And then we can also draw our stress profile, right? If we know the strain, we can use Hooke's law and we can draw our stress profile. Okay, so I have compression at the top, so everything is being pushed this way. This is now sigma max at the very top, this one. And then I have tension. These should be equal. My drawing is a little off, but pulling out. This is sigma max also, and they're equal. And here you can see I'd have some resultant here in tension, and I'd have some resultant here in compression, and the distance between these two, this distance is the arm. And I know here to get the couple, this moment is applied here about the neutral axis. This moment is equal to T times the arm and also C times the arm. This is the definition of a couple, right? Okay, Now, what can I do with this? Well, I can figure out a lot of stuff. I can use similar triangles here. And I can see, well, this is epsilon max, right, up here. So I can say that negative epsilon max, negative because it's compression, negative strain, over C, because this is my C value right here. This is C. And I want to know for any strain at Y, at some distance Y from the NA. Okay, so I can set this up in saying any strain for Y. So this big triangle, make sure you guys are really good at these similar triangles because they've come back a lot. I'm trying to figure out, sorry, different color than what we've used. This is the big triangle, this is the little triangle, and I'm just setting up a similar triangle with those, okay? So I can solve and I get epsilon is negative Y over C epsilon max, okay? And I can use Hooke's law now. We all remember Hooke's law, right? Stress is equal to modulus of elasticity times strain. Okay, and so I can plug all this good stuff in. And I can simplify this, so we're getting really close to our flexure formula. Almost there. The only thing I have to do now is take equilibrium of this stress block up here because I want to relate this moment to sigma. So how can I relate moment to all of these? Well, I take the equilibrium, and this is actually a stress block. So you can see in our slides later, this is actually a stress block. So we're going to take equilibrium of this. So what is equilibrium? Well, we're going to take sum of forces. So let me write what we're doing. Equilibrium of stress block. Okay, sum of forces are equal to 0. Well, that's just sigma dA equals 0. Okay, this is the sum, because we're taking that differential element, of the stress over the entire area. Okay, and I'm going to substitute delta equals negative Y over C delta max in that integral. And I basically get the integral of delta max, sorry, I keep saying delta, of sigma max over C times negative Y dA equals 0. And from here we see, well, sigma max over C, this is a constant. I only have one sigma max value, one C, the distance from the neutral axis. This is a constant. And what can I do with a constant? I can take it out of the integral. Okay, so I end up getting I'm taking the negative sign out, 2 negative sigma max over C integral of Y dA equals 0. And this is a special integral right here. We call this our first moment area. And what we're seeing is this can't be 0, but when is this 0? This value has to be 0 if we're saying that there's an equilibrium, and it's only 0 when the geometric centroid goes through the NA. Okay, so let's continue now with equilibrium, and let's take sum of moments about the z-axis. We have that applied moment m in there. This is y sigma, that's the moment arm y sigma dA. And we're going to plug in what we know here, negative y squared over c sigma max dA. Once again, sigma max over c is a constant, so we can say that m equals negative sigma max over c integral of y squared dA. And this is also something that we know is a special integral. This is our second moment area. Okay, and this is actually our moment of inertia. Right? We all know what that is. That is our resistance to bending or rotation. So resistance, that is the definition of our moment of inertia. Pretty cool, right? So, and you can also see, just as a side note, the higher the I, the higher the resistance. Side note, okay? So now we don't need to actually calculate this double integral in terms of dx, dy. All we have to do is know the moment of inertia of our section, And we can get M equals negative sigma max over C times I, right? So sigma max is actually equal to MC over I. And we drop the negative because we're really interested in the absolute value here. And this is our first flexure formula. And if we want this at any sigma, we can say that sigma is my over I, that arbitrary distance away from the neutral axis. And these are our flexure equations. This is the flexure formula. These are super important for you to know and to understand how we got them. So I'm going to put flexure formula. Okay. You will be expected to know these equations, kind of understand how we got them and where everything came from, okay? So this all now I put for you in kind of a summary from the book so you can see all of these diagrams that correspond to that. You can see the neutral axis really well here, the neutral surface it would be called in this 3D element, okay? And this is what happens when we actually apply that moment about the z-axis and we bend it. So that's what I was saying. Try to make those shapes with your hands and make sure you understand the difference between torque, right, and moment, okay? This is a picture of a wood specimen that failed due to bending. So you can see here what's happening. The top fibers were crushed and torn apart at the bottom here. This is a bending failure. This is a picture of the stress block and a small differential element that we kind of use, this dA, to derive our flexure formula. And here is a really nice summary of our flexure formula and kind of all of this information that you need to know about it. Okay, so we are going to actually stop for this video and we'll continue with the examples in the next video.